Now in this video we are going to discuss about the who's more acidic, right? Alcohols are more acidic, or phenols are more acidic, or carboxylic acid is more acidic. Let me tell you that alcohols are the least acidic. Phenols are a million times more acidic than alcohols. So if I want to write a gradation, so I will say that phenols are a million times more acidic than alcohols. Phenols are a million times more acidic than alcohols. Alcohols are the least acidic, and even more acidic than phenols is carboxylic acid. Because of better resonance, carboxylic acid is even more acidic than phenols. And who's even more acidic than carboxylic acid? It's our mineral acids. They are our mineral acids. Like, who are the mineral acids? HCl, HNO3, H2SO4. Out of that also, out of these HCl, HNO3 and H2SO4, sulfuric acid will be considered to be the strongest acid. Okay, sulfuric acid will be considered to be the strongest acid. See, these are the inorganic acids, okay, and these are the organic. So amongst the organic, alcohol least acidic, then phenol, then carboxylic acid. So what are we going to discuss as of now? Initially we're going to talk about phenol and alcohol. Why phenols are a million times more acidic than alcohols? Let us check why phenols are a million times more acidic than alcohols. So here I have a reaction of alcohols wherein alcohol is donating an H plus ion. So सबसे पहले alcohol is, it's very difficult for alcohol to release the H plus ion, whereas on the other hand, on the contrary, we have phenols, and it is relatively easier for phenols to release the H plus ion. So after releasing an H plus ion from alcohol, it is called as alkoxide. This is called as alkoxide. Alcohol converts into an alkoxide. Okay, and phenol, after donating an H plus ion, will convert into phenoxide. What it will convert into? It will convert into a phenoxide. So we call this as a phenoxide, and this one as an alkoxide. Now you need to observe something. What is that something? That alcohol, it is difficult to donate an H plus ion. Why? Because here there is an alkyl group. Alkyl group is an electron donating group. Electron donating group does not polarize oxygen, and therefore hydrogen cannot be easily donated. Whereas if you see in phenols, the carbon to which OH is attached is an sp2 hybridized carbon. Here it is attached to an sp3 hybridized carbon, an alkyl group, which is an electron donating group. On the other hand, sp2 hybridized carbon is an electron withdrawing group. It will pull electrons from oxygen. When it pulls electrons from oxygen, what's going to happen? It is going to polarize this oxygen. Oxygen will become electron deficient. It will in turn pull electrons from hydrogen. See, the electron density on oxygen will decrease when carbon is pulling electrons. Carbon is sp2 hybridized, it is pulling electrons. The electron density on oxygen will decrease, and relatively it is going to pull electrons from hydrogen. It will pull electrons from hydrogen, kick out hydrogen as hydrogen ion, and those who donate hydrogen ions easily are acidic. That's how oxygen gets polarized, and then it kicks out hydrogen ion to donate hydrogen ion. That is what it is. That's the reason why it is becoming acidic, and it can donate hydrogen much more easily as compared to the alcohols. Okay, so the ones who donate H plus ions, you know from the very beginning that the ones who donate H plus ions are more acidic. So this first thing is the release of H plus ion. First point which we spoke about is the release of H plus ion. So release of H plus ion is much easier as compared to in phenols as compared to alcohols. Why? The reason is sp2 hybridized carbon, sp3 hybridized carbon. Moreover, now talking about the bond length in ROH and CO, the bond length here is shorter. In CO is shorter, and because the bond length is shorter, the carbon holds on to the oxygen more tightly, pulls electrons from it, and makes the hydrogen released. Okay, and that's the reason why phenols can donate H plus ions easily. Now, second thing, first point was the release of H plus ion. Second is the recombination of H plus ion. So what is recombination of H plus ion? Recombination of H plus ion meaning, if you observe the arrows over here, okay, this is a single-headed arrow, this is a double-headed arrow. This is only strictly in comparison between alcohol and phenols. So alcohols, once they give their H plus ions, they have a tendency to recombine with its H plus ion. Why do they have a tendency to recombine with the H plus ion? If you focus on the alkoxide, this alkoxide is having a negative charge resident or localized on the oxygen. So if the negative charge is always being here, so it is but obvious that the H plus ion sometime or the other will recombine with O minus and give you what? Alcohol. That's why the broken arrow is being shown over here. But whereas in phenoxide, this H plus ion will not combine easily with the O minus. Reason being that this negative charge is not permanently on the oxygen. It is getting delocalized. It is getting delocalized something because of resonance. Okay, now because of resonance, what's happening? This is an electron donating group, who? Oxygen, and or OH group is an electron donating group. So what is going to happen is the electrons will be donated towards the benzene ring. This will show positive resonance. In the process, you will get a double bond O, C double bond O over here. And the moment you get that, this negative charge will migrate to the ortho position. The negative charge will migrate to the ortho position. Okay, having a hydrogen over here, this double bond will move out. Okay, and the electrons are moving out. That's why you are having a negative charge on the ortho position. This bond is as it is. Okay, and because there is a negative charge on the ortho position, you can see that the negative charge is not there on the oxygen. That means it has got delocalized. Now in this case, can H plus recombine with the oxygen again? No, it cannot. And this resonance is not going to stop. It's going to continue. From the ortho position, the negative charge is going to move to the para position, and when it moves to the para position, these double bonds will shift over here, and that's the reason why it is moving to the para position, and C double bond will remain as it is. So this negative charge comes now on the para positions, because you can see that this carbon is not satisfied. 1 2 3 is the valency. To help out this carbon, these bonds shift over here. Bonds are nothing but a pair of electrons. So when they shift over here, again the negative charge migrates to the ortho position, and when it migrates to the ortho position, you can see that again the H plus does not stand a chance to combine with the oxygen. Oxygen is still double bond O, and ultimately it will come back to oxygen, and so the chances of H plus recombining in case of phenoxide is very less. Why? It's like it's stronger acid. See, जो strong होता है ना, सलमान खान कैसा strong है, क्या बोलता है, ठीक है, एक बार जो मैंने कमिटमेंट कर दी तो फिर मैं अपने आप की भी नहीं सुनता. सिमिलरली फिनॉक्साइड क्या बोलता है, या फिनॉल क्या बोलता है, एक बार जो मैंने H plus आयन दे दिया तो मैं उसके साथ में रिकम्बाइन नहीं करता. I will not recombine with the same H plus which I have given. So the chances of H plus recombining are less. ये weak है, ये definitely recombine करेगा, but ये थोड़ा strong है उसके comparison में, तो easily recombine नहीं करेगा. So these are the reasons why phenols are a million times more acidic than alcohol. And we also know that carboxylic acid, as we have seen over here, carboxylic acid is even more acidic than phenols. What is the reason? Let us see. Now in carboxylic acid, you can see over here, phenols, there is a resonance in phenols. Okay, but the resonance in phenols is slow. Like, have a look, if you're having a ceiling fan probably above your head, okay, then that ceiling fan, when it is stopped, you can see those 3 blades. But when it is moving at a higher speed, it will look like an apparent circle. So in phenols, when these bonds are moving at a higher speed, it will look like a circle, and that's why we sometimes draw a benzene ring like this or phenol like this. Okay, but the resonance is comparatively slower as compared to the carboxylic acid. So if you have a look at the carboxylic acid, so this is your carboxylic acid. Okay, after it donates an H plus ion, okay, R C double bond O. Now this is an electron withdrawing group. It will withdraw electrons from carbon. Carbon will in turn withdraw electrons from oxygen. Oxygen will get polarized. It will pull electrons from hydrogen and kick it out. And when oxygen kicks out the hydrogen, oxygen gains a negative charge. That's the electron of hydrogen actually, and hydrogen will get a positive charge. And this is donating H plus ion. That means it is an acid. So why is it stronger than phenols? Because the resonance in carboxylic acid, okay, the resonance in carboxylic acid is much stronger as compared to the resonance in phenols. Now have a look. Now this oxygen is saying, yaar kya isko double bond diya, meko bhi double bond chahiye, even I want a double bond. So what is happening? This double bond, carbon says, okay fine, I'll give you the double bond. Okay, so the double bond will shift over here for some time, and this oxygen is getting the negative charge. The oxygen on the top is getting the negative charge. So due to which the bond length, this bond length has decreased, this bond length has increased a little, and this oxygen says that I want my double bond back. I was initially possessing the double bond, so the double bond will again go back, and this, because the electrons are migrating between 2 oxygens, and oxygen being the world's second most electronegative elements, so the pull of electrons by the oxygen is much stronger as compared to the pull of carbon. See, the electrons are being pulled by carbon, so pull of electrons by carbon is very less. Carbon is not that electronegative to pull the electron, so the resonance is there, but the resonance is slower. The electronegativity of carbon is lesser as compared to the electronegativity of oxygen. So what happens if the electronegativity of oxygen is more? It pulls back the double bond more faster. So if you see over here, the double and single bonds swing between the 2 oxygens rapidly. Okay, here they are swinging, but the swinging is slow. Okay, the migration of electrons between the carbons is slow because carbon is less electronegative, but the oxygen is more electronegative, and the electrons, they migrate rapidly. Okay, the double bond migrates rapidly between both the oxygens, resulting in the partial double bond character between both the oxygens. And when both the oxygens receive a partial double bond character, this carboxylate ion, it is called as carboxylate ion, this carboxylate ion becomes more stable. Okay, we'll draw a triple line over here, which indicates that this is the resonance hybrid. These are the resonating structures, and this is the resonance hybrid. The resonance hybrid is more stable. Okay, resonance hybrid is more stable than the resonating structures, and you can see that the negative charge is also being split into minus half and minus half, resulting in greater stability. Okay, resulting in what? Greater stability in case of the carboxylate ion. So the H plus ion, recombination of H plus ion is more difficult in carboxylate ion as compared to the phenoxide ion. Okay, as compared to phenoxide ion. So coming back to our sequence, alcohols are the you can say least acidic, a million times more acidic than alcohols. Phenols and carboxylic acid is even more acidic than phenols. But remember, in front of the mineral acids, carboxylic acid is also considered as a weak acid, because these mineral acids are far more better H plus ion donors as compared to alcohol, phenol, and carboxylic acid all put together. Okay, and they do not accept their H plus ion back as well. So the recombination is also very difficult in case of mineral acids. So this is a video, a note on acidity of different compounds.